All right, guys, you don't even understand. I'm excited. Oh, there's my pen. Before I started, I was like, "Where's the black pen? Where's the black pen? I want to write in black." Um, anyways, guys, this is the best unit in the world. I'm honest to God, I love trigonometry. Trig is one of my favorite things, and I'm being serious. I know I put it on the front sometimes and being jokey, but I do really enjoy trig, and we get to do it now. So today we are going to go through 9.1. Now, before we go through 9.1, I do need to preface this. Always rip off the first page. This is going to be trig is very, even though I enjoy it a lot, sometimes it can be complicated. So getting various different problems to work with and seeing like real life examples is something that's going to come up a lot. Throughout this unit, we will be having a story. Now, the story at hand, we're going to go into more detail in 9.2 when we actually learn everything about trigonometry, at least for this section. I broke up this unit into 3 parts. Once we get through the first part, we'll come back to this unit story. So don't worry about this page for right now. So we can skip that. But for right now, we can start on the first thing, which is the Pythagorean theorem. Now, the Pythagorean theorem is something that you guys have worked with already in years past, but today we're going to kind of fully, I was going to say embrace it, but like we're going to understand why the Pythagorean theorem works today, instead of it being more of told to you. Because we know straight up, like, c squared is equal to a squared plus b squared, but why? Why is it equal to it? Well, it deals with the squares of each of these values of a, b, and c. Now, remembering back to the past unit, we worked with squares when we did area, like when we had to go from 1D to 2D, from like measuring side lengths to the whole area of a polygon, we had to square our ratios. Think of kind of like that when we're working with Pythagorean theorem a little bit. To demonstrate this, I'm going to use Cheez-Its. Now, this is recording. Oh, yo, my dog's going crazy. He's like, I don't like I'm right by the window outside. So he is barking. We're going to be making a triangle with Cheez-Its, and we're going to be proving the Pythagorean theorem with Cheez-Its. Now, I'm going to lay them out like so. So I have a triangle on my paper that has sides of 3 Cheez-Its, 4 Cheez-Its, and 5 Cheez-Its. Now, I mentioned area a little bit with the Pythagorean theorem, and looking at the actual theorem itself up at the top, it states, in a right triangle, the square of the length of the hypotenuse. Also, I did not cover this already. The hypotenuse is the longest side on our triangle, and in this case, it's C. I'm going to shorten hypotenuse with HPY. That's the hypotenuse, and it is equal to the sum of the squares of the lengths of the legs. A lot of those. The legs, in this case, I'll use a different color. It is B and A. These are the legs. They are the other 2 sides of the triangle. These are the legs of the triangle that we're working with. Now, going off of squares and area, I'm given this triangle right here. I'm going to focus on these 2 legs that I have for my Cheez-It triangle. The 3 Cheez-It side and the 4 Cheez-It side. Supposedly, the areas of these 2 Cheez-It sides are going to be equal to the area of this 3rd big side. So let's see. Now, how am I going to find the area of the 3 Cheez-It side? Well, it works off of we're going to build across. see that we have an a squared. Think of our side length as our side lengths given as a, b, c. To get a squared, I have a right. I almost just knocked Cheez-Its everywhere. To get a squared, I have a side length that is already a with the 3-sided right here. I need to add another a side, which is why I started a row of 3 down here. Do a times a, that's going to get the area of this first triangle, of this first Cheez-It side, being 9. I have 9 being my area. Go down here for, I'm going to have to zoom out. Boop. 0.05. Oh, you get to see more of my desk. Ooh. Looking down here, I have 4 Cheez-Its. I have that for my b length. I gotta get b squared, so I gotta add some more Cheez-Its going down like so. And now I can start adding my area in. Now notice that I'm going to have 4x4 for this Cheez-It side, so I'm going to have 16. And I have 9 for my 3-sided one. Now, this next part I did not do in class. Everything's not lined up. This next part I didn't do in class because I didn't think about it, but it works. And it kind of proves my point better for the Pythagorean theorem. In class, I brought more Cheez-Its out and put them all here to kind of prove like, hey, 9 plus 16 equals 25. Because we can apply the same idea, like what we did with these 2 sides to the C side. And we know 9 plus 16 will equal 25. This is a row of 5. If I'm going to get C squared, I'd have to add another row of 5. 5 times 5 is 25. Yada, yada, yada. Instead of making more Cheez-Its and putting them back out here to just have like big Cheez-It blocks, how about let's actually show that a squared plus b squared is equal to c squared. Take the areas of my 2 sides and put them into c squared. So what I'm going to do, I'm going to start breaking apart the areas that I have right now. And we are going to get our area for c squared. This should work out nicely. Cheese it down. It's on the floor. This should work out good. Should work out good. If not, I'm a phony. He's a big, fat phony. Uh-oh. We're missing the Cheez-It. There we go. It works out in the end. Now we have 25. This is 25. 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. 25 Cheez-Its. It works out. It's good enough. So now we know that a squared plus b squared is equal to c squared. It works out in the end. So disregarding the Cheez-Its now, I gotta put them back away. They've been grabbed on too much recently. Hopefully I don't get sick while eating these. That would be very unfortunate. It really would. I do not have the time, and I cannot afford to get sick yet. I'll get sick during spring break, but not right now. I cannot afford getting sick right now. Only in spring break. Zoom back in. I don't want you guys to see my desk. It's a mess. All right. So going off of the Pythagorean theorem, we can say that the area of c squared is the same as the area of a squared plus b squared. We had 3 Cheez-Its, a 3 Cheez-It side right here, which gave us an area of 9. We had a 4 Cheez-It side that gave us an area of 16. And we had a 5 Cheez-It side that gave us an area of 25. And we know 16 plus 9 is equal to 25. Good. Proving our Pythagorean theorem. There's multiple ways to prove this theorem. There's multiple ways to do the Pythagorean theorem, but this is just the way that I chose to do it this time around. So going back on the Pythagorean theorem and kind of working with what we have, we need to know what we're going to list off the sides that we had, like how many Cheez-Its we had per side. In this case, we had a 3 Cheez-It side, 4 Cheez-It side, and a 5 Cheez-It side. This is actually a very important relationship with the Pythagorean theorem itself, because these 3 sides have a special name, and it's called a Pythagorean triple. Now, what's a Pythagorean triple, you might be asking? Well, it's a group of 3 numbers that create a right triangle. And it will always create a right triangle. I'm trying to find a highlighter, but I do not have one in my at-home bin. So we will be circling with red. These are a list of common Pythagorean triples right here. The most common ones are bolded, like 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. And there's all different kinds of variants under below them. But to note, you can make Pythagorean triples by multiplying them out. Like if I have an x of 2, 4, 3, 4, 5, I can multiply 3 times 2 to get 6, 4 times 2 to get 8, and 5 times 2 to get 10. You can do that the same for each and every Pythagorean triple, and you can constantly get a bigger and bigger Pythagorean triple. Again, note that these Pythagorean triples, they create right triangles. One thing to note about Pythagorean triples is the fact that if you are going to get a Pythagorean triple, they have to be whole numbers. You are only working with whole numbers. So you must be a whole number. That means I want no decimals and no negatives. Those cannot make a Pythagorean triple. It's only whole numbers. So numbers from 1, 2, 3, and so on, going all the way to infinity. Only those numbers can make Pythagorean triples. With this in mind, we can go into example 1, and we can find out what x is and decide if these triangles given to us create a Pythagorean triple. Now, working this out, I can do... before we even start with that, I need to mention one thing, which is the case of the letter C. I mentioned it already, but C is the hypotenuse of our triangle. Of our right triangle. It's the hypotenuse, which is the opposite side of our right angle. And it's also the longest side. So when we're working on trying to find Pythagorean triples and trying to see if something's a right triangle, we have to keep in mind we have to find out what C is. So looking at A, I have a 4, a 5, and an X. I don't know what every value is on this triangle itself. But what I do know is that I can find the hypotenuse, find the C, by looking opposite from my right angle. What I can do is I can make a point down here at that right angle, and I can draw a line to the next side, or to the side across from it. That's going to find the opposite side from the right angle, and that's going to be my C. So X is going to be my C value. So when I set this up, doing C squared is equal to A squared plus B squared, I will end up having X squared is equal to 5 squared plus 4 squared. For right now, it doesn't matter what we have for A and B. I can have 5 at A or 5 at B, but for right now, you can interchangeably put them wherever you want. So now I can start trying to solve for x. For right now, I'm going to keep x alone, so I'll have x squared, but I can simplify down this 25 squared and 4 squared. So I'll have a 25 plus 16. And now I can combine both of them together to have x squared is equal to 41. And I can find this, and remember, and going off of stuff we did with radicals and simplifying, I need to get rid of this square root off of my x squared. To get rid of, I need to get rid of this square off of my x. To get rid of that square, I gotta cancel it out somehow. To do that, I'm going to take the square root. Square roots and squares cancel each other out. If you need to make a note of that, write it down. One thing to note, and you can look at your calculator for this. These two things are inverses of each other. Like on our calculator, a lot of our symbols have inverses of each other that are in the blue. So like the inverse of a square would be a square root. And there's a whole bunch of other inverses, and some we'll go into in this chapter, some we will not. But inverses are a thing, and a square root and a square are inverses of each other. So that's how I'm going to cancel out this square. So I take the square root, and I'll end up with an x that is about 6.40. So looking at what I have, so looking at the sides that I have a 4, a 5, and a 6.40. Now, I need to decide if this is a Pythagorean triple or not. Looking back at what I have, I can only have a Pythagorean triple if I have sides that are whole numbers, which means no decimals, no negatives. What I have here, I have a 4, a 5, and a 6.4. This 6.4 is a decimal. So that means I have no Pythagorean triple. So I'd write not a Pythagorean triple. And that would be our final answer. Now looking at example 2, we have to find out what y is. I did not say it was an x because I didn't care. Anyways, I need to find out what y is. That's my missing value. And after I find out y, I can determine if it's a Pythagorean triple with the 3 sides. I need to find out what c is first. So I'm going to go opposite of my right angle. And in this case, it is going to be 25. So that means 25 is going to be the biggest side length on this triangle. So when I set up my c squared is equal to a squared plus b squared. What happened to my blue? Oh, it's right here. That means I'm going to have 25 squared is equal to 15 squared plus y squared. And then getting all of that into a nice, comfy, I don't know. I'm going to square it. Turn on the calculator. 25 squared. 625. That'll be equal to 15 squared, which is 225. And that is plus y squared. I can subtract 225 on both sides. And that will give me 400 is equal to y squared. And I can take the square root of this y squared to cancel out that squared. And I'd end up with a 20 is equal to y. So that means for the side lengths that I have 15, 20, and 25. This ends up being a Pythagorean triple. Actually, if we work off of what we know up here, this would actually be x equals 5 for a 3, 4, 5 Pythagorean triple. Fun fact. So yes, this is a Pythagorean triple. Now, with working with the Pythagorean theorem, story problems happen. Of course they do. Come on. What's a math lesson without story problems? Come on, bruh. In this case, we have a flagpole that's supported by 2 wires. Oh my god, 2 wires. And I want to find the length of those wires, and I have to use the Pythagorean theorem to help me with it. Oh boy. Let's zoom in a little bit so we can actually see it. So I have the flagpole at a height of 15.1 feet tall. We also have 18.5 feet from the end of the wire to the flagpole base itself. And I need to find how big this wire is. Now, this 15 feet can be moved onto the inside, or 15.1 feet, can be moved onto the inside of my flagpole. And this is a right triangle, so I can use the Pythagorean theorem to help me solve this problem. Now, one thing to note is that x, in this case, is going to be our biggest side length. So when I write this out, it would be c squared is equal to a squared plus b squared. Subbing in what I know, I'd have x squared be my c squared. Since it is opposite of that right angle, it's the hypotenuse of this right triangle, so it's going to be c. And it'll be equal to 8.5 squared plus 15.1 squared. Now, if I square these boys out, I will have x squared is equal to 72.25 plus 228.01. Adding those together, that will be 326. 300.26. And then I can take the square root to cancel out that square and find out what x is, which will be about 17.31 feet. Nope, 17.33 feet long. Now, and you might be wondering, like, oh, dude, you have a decimal. What are you doing? Well, I'm not finding a Pythagorean triple. I'm trying to find out how big this wire is. I'm not finding out a triple, so it's okay if I have a decimal. I know in class we were a little confused on that concept, but it's okay. But that's not too bad. We've done a lot worse. Pythagorean theorem stuff is fun. Well, I wouldn't... No, it is fun. What am I saying? What am I saying? I love trig. But with a theorem comes the converse of it. In the fact that if I have a statement that says c squared is equal to a squared plus b squared, if I have values that represent that, then that means I have a right triangle. So you get a right triangle. We're going to actually practice this and you'll kind of understand what I'm saying. All right. First off, this is going to deal with a bunch of radicals. Do not use decimals in the Pythagorean theorem. Not allowed. If you do, I will mark that whole answer wrong. Anyways, let's get started. So I need to tell whether this triangle is a right triangle. To do that, I need to see if c squared, our longest side, is equal to the sum of a squared plus b squared. If this is true, then I get a right triangle. Looking at example A, I have the side lengths 8, 12, and 4 square root of 5. I need to figure out which side is the longest side. That's going to be my c value. This is the only time I will ever let you use a decimal with a radical, because you need to figure out what 4 square root of 5 is. You don't know that off the top of your head. So take your calculator and you plug it in. This brightness is very big. So we'll do 4 square root of 5. And we get 8.944. So this is 8.94. And which one's the biggest side? Well, it's 12. 12 is the biggest side. That is definitely the biggest one. So that means that is going to be my C value. So that means when I write this out, we have C squared is equal to A squared plus B squared. 12 is my C value. It is my longest side length. So I'm going to have 12 squared is equal to 8 squared plus... Do not use this decimal. Like I just said, if you use it, you'll get it wrong. I will mark it wrong right away. You got to use the radical. So you will have 4 square root of 5 squared. This is why we had that radical day where we were simplifying radicals, making everything small. Because you have to do it here. So, 12 squared, that's 144, is equal to 8 squared, 64, plus, now I have to deal with this. What I have to do, I need to take this square right here, and I need to distribute it out to each of the terms inside of my parentheses. So this squared is going to go to the 4, and it's going to go to the 5. So I'd end up with 4 squared, which is 16, but we'll write out 4 squared, times the square root of 5 squared. Rewriting this. 144 is equal to 64 plus 4 squared is 16 times, I have a square root squared, so that means these two cancel each other out. So I'd end up with just 5. I have 144 is equal to 64 plus 16 times 5, which is 80. And adding those together, I'd have 144 is equal to 144. So that means this triangle is a right triangle. So I can say, yes, a right triangle. Yay! All right, on to B. We need to figure out which side length is our biggest. Opening up our calculator again. We have 2 square root of 30. Adding a parenthesis because I'm crazy like that. So I have 10.95. That is not the biggest side length we have. So 14 is going to be our C value. So I have C squared is equal to A squared plus B squared. And then I have 14 squared is equal to 9 squared plus 2 square root of 30 squared. I'm going to go a little faster. We have 14 squared, which is 196, is equal to 81 plus 4 times 30. Because the square is going to get distributed out to both the 2 and the square root of 30. So then I end up with 196 is equal to 81 plus 120. And summing everything together, I would get 196 is equal to 201. That is not the same number. They are not equal to each other. So that means this is not a right triangle. But hold on a minute. It is a triangle, though. It is. It is actually an acute triangle, if we want to be specific. Why do I say it's an acute triangle? Well, we're about to go into it. Now, I'm going to do both day 1 and day 2 in the same video, but we need to take a step back, a stroll back to chapter 6, where we started determining whether something was a triangle or not with the triangle inequality theorem. This theorem stated that the sum of lengths of any two sides of a triangle is greater than the length of the third side. What does this mean? Well, let's give these side lengths some names, like C, B, and A. That's not right. This one is A, this one is B. This one is C, though. What this theorem is stating is that if we have A plus B, B greater than C, if we have A plus C be greater than B, and if we have B plus C greater than A. If two side lengths added together is greater than that third side length, and all the statements are true, then that means ABC is a triangle. Cool. This is part 1 of the theorem that we're about to work with, which makes this triangle make sense, because this is a triangle, but we don't know what kind of triangle it is. We're about to get into it. But before we go into the actual theorem itself, I do want to have a little bit of practice on finding out if something's a triangle or not. So let's try it out. We need to determine if the 3 given side lengths we have make a triangle or not. So we need to check if 4 plus 9 is greater than 10. It is, because this would make 13, and 13 is definitely greater than 10, so this statement is true. Now we have 9 plus 10 is greater than 4. We know that this would make 19, and that is definitely greater than 4. Now we have, 10 plus 4 is greater than 9. This would make 14. 14 is greater than 9, which is good. So that means that these 3 side lengths make a triangle. So this makes a triangle. Cool. What about this? Let's check. 5 plus 7 is greater than 12. 5 plus 7 is 12, which is greater than 12. Huh. All right, what if I'm in a situation like this where both sides equal each other? Well, in the theorem that we just wrote down and kind of worked out a little bit, I do not say anything about equals to or less than. Only greater than, strictly greater than. These 2 side lengths, when they add together, they equal the third. This is not allowed. So that means that these do not make a triangle. So if you need to make a note, strictly, that's not how you spell strictly, greater than, never can be equal to or less than. If you need to write that down, please do it, because it's important. Because some of our problems are 2-step processes. So it's important to know how to actually work with it. Going forward, we're going to take this idea of determining if something is a triangle and then making its classification, whether it is a right triangle, an acute triangle, or an obtuse triangle. We do know what an acute triangle and an obtuse triangle are. We did that in Unit 5. But we're going to do some classification, because we do know that there are different kinds of triangles other than a right triangle, as seen in this example right here. This is a triangle for sure because it has 3 sides, but it's not a right triangle. We just determined that. So let's see what we could actually do and make of it. So with the Pythagorean inequalities theorem, we have 3 statements that can be made. One of them being is that if c squared is less than a squared plus b squared, then that means ABC is going to be an acute triangle. If we have c squared equal a squared plus b squared, then that means our triangle ABC will be a right triangle. And if c squared is greater than a squared plus b squared, then this is going to be an obtuse triangle. One thing to know, and something that is clever about the way we write the Pythagorean theorem, is our placement on C. If we know that C is always going to be less than our sum, then it's going to be acute. So think of if C is smaller then it's going to be acute, because acute is the smallest kind of triangle, has the smallest angles. If C is going to be bigger than our sum of a squared plus b squared, it's going to be greater than, then that's going to be obtuse. It's going to be the biggest, so it's going to be the biggest kind of triangle, the obtuse. It has the biggest angles. Little neat way of remembering how the inequalities will be working. And we can put this into practice with example 2. We need to first verify if these 3 side lengths given to us make a triangle, and if it does, we have to determine if it's acute, obtuse, or a right triangle. First, we need to check if 14 plus 15 is greater than 11. That means we have 29 is greater than 11, so yeah, that statement checks out. That's definitely how it works. Now we need to check if 14 plus 11 is greater than 15. That would mean it's 25 greater than 15, and that is also very much true. And let's check 15 plus 11 greater than 14. That makes 26 is greater than 14, which is also a true statement. So that means all 3 side lengths check out. It makes our theorem true. So we are dealing with a triangle. Yay. So I'll just make a note that yes, a triangle. You do have to tell me if this is a triangle or not. So don't be like, nope, you can't. Nope, I'm not going to do that. No, you have to. You gotta tell me if it's a triangle or not. But now let's determine if it's acute. Before moving on, I need to first find out which side length is my C value so that I can use the Pythagorean theorem. Remember, C is going to be our biggest side length, the biggest number. In the case of 14, 15, and 11, 15 is our biggest number, so that's going to be our C value. So when writing out my Pythagorean theorem, I'd have 15 squared. And I don't know what my symbol is going to be yet, so I'm going to put a box in place of a equal sign, a less than sign, or a greater sign. I'll fill that in once I know what I'm finding. And then I'd have to fill in 14 squared plus 11 squared. Now I can start squaring everything and then simplifying to see what numbers I get. So 15 squared would make 225. 14 squared would make 196. And 11 squared would make 121. Adding these two together, I'd get, I don't know what, like 317? Yep. I get 317. All right. And now I need to determine what inequality sign I'm using. It's definitely not equals to because these numbers are not equal to. But I do know that 225 is a smaller number compared to 317. So what I can do is use the less than sign right here. Because 225 is less than 317. And since I'm using the less than sign, and my C value is less than my sum, that means this triangle is an acute triangle. And that's it. Not too shabby.